Hello everyone. In this video we'll take a look at calculating water surface profiles using standard step and direct step methods. In the first problem you see in the screen, we are given a channel geometry including some properties of the channel. We are also given the normal and critical depth, and we're given depth at a location as well. So using the relationship between y and y critical and y normal, we should be able to determine what the curve type is going to be. So in this case, y is greater than y critical and y critical is greater than y normal. So from this one we can tell the channel is steep, and since the depth is greater than either of those, we know it's a S1 curve. So on the channel side view, the curve will look something like this. And if the location of the given depth y, which is 1.79, is here, we would like to find the depth at a point upstream 5 meters from the previous depth location. So this is the first, this is the depth that we would like to find out. So once we know what the curve is like, and we can then think about the different parameters that we'll need to calculate in solving this problem. So standard step method, if we just step back, so let me just go back and set up the standard step method. So we start with total energy downstream, or rather start with upstream, equals total energy downstream plus any energy lost going from upstream to downstream location. We can break these further into their components. So Gu plus Yu plus V squared over 2Z equals Gd plus Yd plus Vd squared over 2Z plus head loss. Head loss can be expressed as the product of average slope of the energy grade line times delta x, which is the distance between the two y locations. Okay, so this basically forms the driver in the way we'll set up our table. So to get the slope of the energy grade line, we'll use Manning's equation, and we can equal this to n squared v squared over, the coefficient here is 1 for SI unit, so it's just 1 squared, which is equal to 1, times hydraulic radius to the power 4 over 3. In this problem in particular, we already know the downstream depth. If we consider the downstream location as having elevation of 0, we can just call that datum. So we know that at a distance of 5 meters, we can also calculate this using the channel bed slope. The velocity at the upstream location is also a function of yu. So embedded within the vu is yu. And with this, I think we can start setting up the table. So section will first enter the water depth. So since we know the downstream water depth, we'll start with downstream and then follow with upstream. This will have units of meter. 1.79 is our known depth. G in meters. So for the datum, we'll start with 0. We can then calculate the cross-sectional area based on y. And let's just write down the equations down here. Area for a rectangular channel, so trapezoidal channel, is equal to yb plus my squared we can then calculate similarly the weighted perimeter for the channel, and that's going to be plus 2y square root 1 plus m squared. Since we are already given the discharge and we calculate the cross-sectional area, we can also get our velocity. Velocity is going to be q over a. Once we get velocity, we can then get our velocity head, v squared over 2z. After we get our area and weighted perimeter, we can calculate the hydraulic radius, and that is going to equal area over perimeter. And I already mentioned it up here, but the slope of the energy grade line at any location can be calculated using this equation. N squared v squared over RH 4 over 3. So this comes from Manning's equation. Once we get the slope of the energy grade line at the upstream and downstream location, we can get the average. So the average, or let me just write it this way with a bar on top. This will equal SE upstream plus SE downstream divided by 2. So using these equations, then we can start filling up the rest of the table here. So area will get a value of 12.154. Velocity, so this is going to be meters squared, velocity meter per second. We'll get a velocity of 3.291. The weighted perimeter will be 10.063. The hydraulic radius with units of meter is going to be 1.208. The slope of the energy grade line in the downstream location is going to be 0.00102. Once we get a value for the energy slope of the energy grade line for the upstream location, then we can also get the average there. From this point on, once we don't have it yet, but once we have the SC average, we can then get our head loss value, and then we'll see we'll compare the total energy upstream to the total energy downstream. And the idea with standard step method is we'll want to pick a value of y upstream such that the energy upstream equals energy downstream plus the head loss. So this one is an iterative process because the velocity and other parameters depend on our choice of y. We'll have to improve our value of y until the energy criterion is met. So as you can see from the setup, this is best done on an Excel sheet. So I have a Excel file here set up. Okay, so this is the setup, and here what you can do is we know the depth upstream is going to be less than the depth downstream, so we can start with the same value, let's say from downstream 1.79, and the difference here is not exactly 0, so this is the difference between the total energy upstream and the sum of total energy downstream plus the head loss. Let's try a smaller value, 0.75, and see if this value so once I change my value from 1.79 to 1.75, the difference is smaller, so we're in the right direction. So let me reduce it further. So 1.7 will make the difference become even smaller. So we can do that until the difference starts increasing again. 6.9. I think that was smaller yet. So this is the way iterative process that you use to find the depth at a given distance from a location of known water height. The other way you could do this is using goal seek. So if you go to data on what if analysis, you can find the goal seek option here, and let me start with the initial value of 1.75. So the way goal seek works is you wanna, so I'm interested in setting the value for this equal to 0. So when that value is close to 0, then that will give me the right y upstream. So we want to get that difference close to 0 by changing this cell. So when you click OK, it will go through iterative process and give us a y value that will result in the list difference. And of course it's not going to be perfect, but it will give us a much better answer than we could using calculator, and it's also a lot quicker. So again, just want to point out this one here is sum of zd plus yd plus vd squared over 2z, and this value here is zu plus yu plus vu squared over 2z. This head loss value gets added only to the downstream total energy when we are trying to look at net energy. So this one here is the sum of the total energy at the downstream location plus the head loss, and this value here is the difference between the sum of total energy in the downstream end plus the head loss and the total energy in the upstream point. Okay, so is there anything else we're trying to find here? Okay, so 1.692 is going to be our answer for this problem. 1.692. The G here is going to be upstream. So the G upstream is going to be slightly higher since the channel is sloping upstream, and since we know delta x, we know the slope of the channel bed, we can multiply. So this value here, actually did I write the equation down here? Okay, so let's just add that equation down here. So Z upstream equals Z downstream plus channel slope times delta x. We know delta x is 5 meters. We're given S0. We picked our downstream Z as the datum, so that is 0. We can calculate our ZU using this equation. 0.020, and you can fill out the rest of the numbers here. So the total energy there, and how is it best to do it? So let's do H, maybe H total, to include the head loss and then the difference here. You can go back to the Excel sheet that I had here before to get the numbers here. So it's best done in Excel. It's actually any other than Excel would be a cumbersome task. But the next problem we'll look at is the direct step method. That one is a lot more straightforward and something you can do on paper. So this here is your final answer. Problem 2, we have a trapezoidal channel. The channel geometry information is given: channel width of 18 feet, side slope of 2. We know the channel bottom slope. We have Manning's roughness value. We're given the discharge and the normal depth. So what we're not given here is critical depth. So in this situation, we will find the critical depth first. So we start with Manning's equation. Here the units are the British units. So we'll make sure we include the 1.49. For our trapezoidal channel, you can get the cross-sectional area. B plus my times y divided by, actually that's area. Perimeter is given by the equation b plus 2y root under 1 plus m squared. So using the m value, the y in Manning's equation, when you use the channel slope bottom, that is the normal depth. So this will, once you plug in the values for area, hydraulic radius, and channel slope, and solve for yn, you'll get the same y1 value up there, so 5.16 meters. So if the normal depth wasn't given, you can calculate it that way. For critical depth, use the critical depth conditions. So for critical depth, it should satisfy this equation: q squared over g equals cube of the cross-sectional area divided by the top width. So the top width is this width at the top. And T equals B plus twice of this length here, which is equal to my squared. So B plus 2 my, actually this my. So we'll use that equation for T. We have Q of 800. G is 32.2. Area, which is the same equation here, except the y is going to be y critical. Our B value here is 18 feet, so 18 plus m is 2 y critical times y critical divided by the top width, and that was B plus, we already know B, 18 plus 2 times m, which is 2 times y critical. From this we can solve for y critical, which is going to be 3.45 feet. Once we have normal depth and critical depth, then we can assess if it's mild or critical or steep or any other channel. Here y normal is greater than y critical, so that makes it a mild channel. So in this problem we start at the brink. So this channel ends up in a waterfall at the end. So, and we found the critical depth is less than the normal depth. So if that's your critical depth, then at the brink the water is going to be at, or close to the brink, the water height is going to be close to the critical depth. So the water will come at normal depth, or actually let me start from the critical depth point at the brink and work our way upstream. So it will look something like this. It will approach the normal depth at a very small angle and stay at the normal depth once it gets to that height. So this is what the flow looks like for this problem. This curve here is going to be M2 curve. So just like the last problem, the equation that we use for direct step method comes from energy conservation. So we can start with the same energy equation and work our way into a workable form of the equation. Okay. Using the energy conservation from upstream to downstream section, we can write H upstream equals total energy downstream plus the energy lost. We can expand this into Z upstream plus Y upstream plus V upstream squared over 2Z equals Z downstream plus Y downstream plus V downstream squared over 2Z plus the head loss term. The head loss again can be expressed as a product of the average slope of the energy grade line times delta x, which is the distance that we want to find out between two known y values. So the difference from standard step method is, in this case, we know both y in the upstream and downstream location. And this, if you notice, is the specific energy. So we can call that EU and call this ED, the specific energy upstream and downstream. And you can rearrange this equation to finally get the workable form of the equation. So if you express this in terms of delta x, you should get ED minus EU over S naught minus SE average. So we'll use this equation to guide our table for direct step method. So we start with section again. Y. And let me add the units. So in this case, we have feet. The next variable we'll calculate is the area, feet squared. We'll then get the perimeter with units of feet. Once you get the area, cross-sectional area and wetted perimeter, you can get the hydraulic radius with units of feet. Given Q and the area that we just calculated, we'll be able to calculate the velocity in feet per second. Once we get the velocity, we can get the velocity head in units of feet. And once you have the water depth and the velocity head, you can get the specific energy in feet. We can calculate the slope of the energy grade line at any location. And then finally we can calculate the distance of a y downstream location, provided we can then find the distance to between those two known water depth values. So in this problem in particular, we are also asked to find the distance from the brink. So distance to brink. So if we start with so let me just go back here and add what the problem is asking us to find. So from the brink, we would like to find out the distance to 3.65. So let's say that's 3.65. So delta x 1, and then we'll also want to find distance to where the water depth is 3.85. So that's going to be another distance of delta x2. So the first depth we need to find out is going to be delta x1, and the location of the next y value, which is 3.85, is going to be at the distance of delta x1 plus delta x2. Just like the last problem, let's just write the equations underneath here that we'll use to calculate the different variables here. So area for a trapezoidal channel is B plus my times y. Let me make sure the equation is correct. Okay. The perimeter is going to be equal to b plus 2y square root 1 plus m squared. Once we get the area and weighted perimeter, we can get the hydraulic radius. The velocity is going to be equal to q, the discharge, divided by the cross-sectional area that is just calculated. And we know what specific energy is. SE again is going to be equal to n squared v squared over, since this is in British units, it will have 1.49 squared times the hydraulic radius to the power 4 over 3. Okay, so let's start with the upstream location. We have 3.65. Using that water depth, we can calculate the area, 92.35, perimeter, weighted perimeter of 34.343, hydraulic radius, let me erase that one digit, hydraulic radius of 2.69, using the area and discharge provided, we can get the velocity. It comes out to 8.663. The velocity head then becomes 1.165. The specific energy then can be calculated to be 4.815, and SC is going to be equal to 0.00361. And we can actually add a new column here for SC average. Okay, so then for the downstream portion, the water depth is equal to the critical water height, which is 3.45, and using this y value we can calculate the whole range of variables here. Area will come out to 85 0.91, weighted perimeter of 33.43, hydraulic radius of 2.57, and we'll get a velocity of 9.313. The velocity head for the downstream end is going to be 9.313. Actually, that's not right. It should be 1.346. We'll get a specific energy of 4.797. The slope of the energy grade line at this point is going to be 0.00444. Let me erase these equations. Okay, so the average of these two values, so let me just write down here because I don't really have space here. So this will result in SE average of 0.00403. 0.00403. Now, using the equation that I put up here, we know the specific energy downstream, we know the specific energy upstream, we know the channel bed slope, we just found out the average slope of the energy grade line. So that'll give us a delta X of 6.183. And this one from the brink itself is going to be the same distance. So if we are to put this at a proper location, we are probably better off putting the delta X here with the upper section 6.186, and the brink is at a distance of 0 from itself. And so distance to brink is going to be 6.186. Now we'll repeat the same steps for the next section. So for the next section, the downstream and the upstream from the first part is going to be this downstream for that. So the upstream is going to be 3.85, and downstream is going to be this value here. So we'll just use that here, 3.65. So we can then repeat same process as the first one. And that'll give us SC average we'll get a SC average of 0.00329. And from that we can calculate delta X. So from the downstream location to itself is 0, but the upstream section is going to be equal to this SC average value actually, yeah, we just go back to using this equation here and get our delta x for that. And that'll come out to 21.687. 21.687. So then the distance to brink is going to be 21.687 plus 6.186, which is equal to 27.87. 27.87. And the distance from brink for the downstream section is going to be 6.186, same as the one before. So this gives us the answer for the second problem. Okay, I'll see you on the next video.